We'll wrap up 3, 4 other tests for zeros and polynomials. Okay, so we've talked about an nth degree polynomial having n solutions, right? Whatever the degree is, that's how many solutions there are. I guarantee a 12th degree polynomial has 12 solutions. Okay. An nth degree polynomial function has at most n real solutions. What that means is if I have a 12th degree polynomial, it is possible that that polynomial has 12 real solutions. However, it's possible that that 12th degree polynomial only has 8 real solutions and the other 4 would be complex. Okay, so that's what this is saying. That's why it says, of course, many nth degree polynomials do not have that many real zeros. For instance, f of x equals x squared plus 1. That is a quadratic that opens up, shifted 1 unit up. So you know that will never touch the x-axis, correct? So though it's a second degree polynomial, it does not have 2 real solutions. Yes, ma'am. Okay, so though x squared plus 1 does in fact have 2 solutions, none of them are real. So it's got 2 complex solutions. X cubed plus 1. X cubed plus 1 does in fact have 3 solutions, but think about what x cubed looks like. It only crosses the x-axis once, doesn't it? So it's been shifted up once. So it still has 1 real solution, the other 2 are complex. Friday, we talked about rational zeros, right? We talked about P's and Q's, P divided by Q. Take the last number, find all the factors of the P, divide that by the factors of Q, and those are your possible real roots. We're now going to introduce the Descartes rule of signs. The Descartes rule of signs is going to tell us more about what those real zeros might look like. Specifically, we're going to be able to determine how many possible positive real zeros there are and how many possible negative real zeros there are. So y'all just hang on. This is about to get very wordy, but once we do an example, it might make a little bit more sense. I shouldn't press forward. Did I do that twice? Let me get back to where we're supposed to be. And here's the wordiness of the Descartes rule of signs. I've got a polynomial. This is an nth degree polynomial. It has real coefficients. The leading a sub 0 is not 0, meaning the constant is a real number. Okay. The number of positive real zeros is equal to the number of variations of the sign or less than that number by an even integer. What the heck did I even say? Okay. All right. What we're looking for is we're looking for sign changes. So if f of x was, I'm just going to make something up, x to the 5th minus x to the 4th minus 2x squared plus 3. Okay. What's the sign of the first term? Positive. It's now negative, and it stayed negative, and it's now. How many times did the sign change? It changed here, and it changed here, right? It went from positive to negative, and then it went from negative to positive. So how many sign changes was that? 2 sign changes. Which means this polynomial has either 2 real positive solutions or 0 real positive solutions. One's not an option. 2 or none. Okay, you're going to see things happening in 2s a lot when we're talking about solutions. Number 2 says the number of negative real zeros of f is either equal to the number of variations of sign of f of negative x or less than that number by an even integer. So here we go. What happens here is if I was using the same function here, I'm going to take f of x, but I'm going to change it to f of negative x. Okay? So that means I'm going to have negative x to the 5th minus negative x to the fourth minus 2 times negative x squared plus 3. What happens when you take a negative number and raise a negative number to an odd power? A negative number to an odd power stays negative. Okay? So notice that this was x to the fifth. What is it now? Negative x to the fifth. This was negative x to the fourth. Okay. What happens when you take a negative x and raise it to an even power? It becomes positive. So this is a positive x to the fourth, just like this one, so it's the sign stays the same. How about this negative x squared? What's going to happen to the sign? It's even, so it stays the same. And that has nothing to do with x, it's plus 3. So what sign changed? The only sign that changed is the one that had an odd exponent. See that? The only sign that changed is the odd exponent. This sign changed. This one stayed the same, this one stayed the same, this one stayed the same. Okay? Now that we have changed the signs on the odd exponents, now let's count sign changes. How many sign changes do you see here? 1. So that tells me that this polynomial, this is the polynomial that I'm working with, not this one. This polynomial, 1 sign change. And I changed to red for negatives, okay? Which means this polynomial has 1 real negative 0. Okay? So I have either 2 or 0 positive real zeros. I guarantee I have 1 negative. So right here it says a variation of sign means that 2 consecutive coefficients have opposite signs. Okay. How deep's the water getting? Is it pretty deep? Yeah. Okay. When using the cardinal rule of signs, of 0 a multiplicity k should count as k zeros. For example, x cubed minus 3x squared plus 2. Okay, question number 1, how many zeros does it have total? 3. Highest degree is 3. This thing has 3 zeros. We haven't talked about anything being real or imaginary or positive. And all we're saying right now is this is a third degree polynomial that has 3 solutions, correct? Okay, if we factored this, this factors into x minus 1 times x minus 1 times x plus 2. Let's go back and apply Descartes' rule of signs to this. Change back to blue. Okay, how many sign changes are there? What's the sign of the first term? Positive, and then it went to, that's 1 sign change. Does it change again? Okay, so that means we have 2 or 0 positive real solutions. Now, I do want to say one thing here. It is possible that these real solutions are not rational. It is possible that there's a square root or an irrational solution, okay? So I have either 2 or 0 positive real solutions. Let's change signs. Anything that has an odd exponent, we're going to change signs. So this was positive, x cubed. Is it still positive? No. 3 is odd. So this guy's going to become negative. This is odd. So this guy's going to become positive. And this one's positive. How many sign changes? It started negative, changed to positive, stayed positive. How many times did it change? Once. This has 1 negative real solution.
Hey, why is this one negative but the other one positive? I don't see much of a difference because the first, so leading coefficients on both of them. Negative.
The leading coefficient here is positive.
So wait, so the
Right, but whenever you flip the spot.
It became negative.
Right.
another relation, so negative to positive.
So I started off negative. My first term is negative.
Right.
The second term is,
Positive.
that's one sign change.
Okay.
And we say positive.
Yeah, but why is this one negative but the other one positive?
Like we talking about the previous problem? That's positive, then negative,
Right.
then positive. It
Right.
changed signs twice.
Right. It has the two sign changes like the other one.
Or zero.
So would it be positive and
Yeah.
is it positive?
Positive.
So you can tell if it's like negative or positive by the leading coefficient, like if it's.
So we have one negative. Real. I'm gonna call it something different this time, zero.
Okay, that makes sense.
Okay.
Yeah, that makes a lot of sense.
Okay, sorry. So they've already factored this one for us. Okay, when they factor x cubed minus 3x plus 2, they get x minus 1, x minus 1, and x plus 2. It does in fact factor into three pieces, doesn't it? That's all three zeros. All three of them are real, but look at this. What does this one tell me? X equals
X equals 1.
1. What's this one tell me? X equals 1. Folks, that is in fact two positive real solutions, even though they're the same. Okay, that is two. That's not just one solution, that's two solutions. What is this one? That is negative solution. Okay. So the two positive real zeros are x equals -1 of multiplicity 2. So last week when we were talking about the rational zeros theorem, we're making a list of possible rational zeros, right? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. That's what we did when we were doing 6, right? If I'm using the Carr's rule of signs in conjunction with the rational zeros theorem, I'm probably not going to try a negative number. Can you see why I might not try a negative number? There's either two positive or none. Would it be a good idea to try negative numbers? I guarantee there is a negative solution. I would use negative numbers with my synthetic division. I would put -1 in that box and see what happens with synthetic division. Okay, so that's where this is headed. We're using the rational zeros theorem along with the Carr's rule of signs, along with synthetic division to find the zeros of a high degree polynomial. That's what we're doing. Describe the possible real zeros of this function. 3x cubed minus 5x squared plus 6x minus 4. Let's count the sign changes. First term starts off positive. Positive turns to negative. That's a sign change. Do you have another sign change? Negative turns to positive. There's another one. Any more? Positive changes to negative. What's that tell me? Okay, so we have 3 sign changes, which means I'm doing the positive side right now. 3 sign changes. That means that we have 3 or 1 positive real 0.
How come it's not 0 positive 0?
You count by twos. Whatever number you start with, you count down by twos. The next number will be -1, and that makes no sense. We can't have negative zeros. Okay. Let's change our signs. Let's try the negative side for Descartes' rules. What does 3x cubed become? It becomes negative, right? So this is going to be negative. How about the 5x squared, negative 5x squared? Stays the same. 6x becomes negative. -4 stays negative. What signs change? To get from the blue to the red, what signs change again? Odd exponents. Odd exponents change signs. Everything else stayed the same, right? 5x squared stayed. -4 stayed. Now, looking at the red here, how many sign changes? None. We have 0 sign changes, which means 0 negative real zeros. So going back to our possible rational zeros, would you want to put a negative number in the box to do synthetic division on this problem? No. Huh? Yeah, there's not any. Would we use positive numbers? Of course we would. There might be, all 3 of them might be positive and real. Okay. In fact, I guarantee there's at least one. Right? It's odd. It's got to cross the x-axis somewhere. This tells us it crosses in the positive direction. So not getting any clearer. It's getting any deeper. Okay, here's our work for showing me change the signs, where they're showing me actually plug in the negative x and they're cubing it to show you what happens. No sign changes. We have no negative real zeros. The way technology is going in here would not surprise you. There's the graph. This graph only touches once. What does that tell you about the other 2 solutions?
They're not real.
Yeah, there's 2 complex solutions, right? Okay. Another test for zeros of a polynomial function is related to the sign pattern in the last row of the synthetic division array. Okay. What's that mean? I'm just going to make something up, okay? Let's say that, let me finish reading this and then I'll make it up. The test can give you an upper or lower bound of the real zeros of f. A real number c is an upper bound for the real zeros if no zeros are greater than c. Similarly, c is a lower bound if no real zeros of f are less than c. Okay, I've got some number. And I'm doing synthetic division. And I don't know what these numbers are. I'm just going to put something in there to hold place, okay? So we do synthetic division. Let's say that this number comes down into a 2, and we do all the synthetic division, and we get something like this. Every one of these are positive, right? Okay. I guarantee that, okay, so 3 is a solution, correct? To this polynomial. 3 is a solution because the remainder is 0. Okay. 4 will never be a solution to this polynomial. Neither will 5 or 6 or any other number higher than 3. 3 is the largest solution. Okay. Well, how can I tell that? Okay. Well, I have the remainder 0. Let's go to the next slide here. If c is greater than 0, and each number in the last row is either positive or 0, then c is an upper bound of the real zeros. So for the example I just gave you, 3 is a solution to that polynomial. 3 is the biggest number that's a solution. So if I was choosing, again, rational zeros theorem, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, should I try 6? No, because this tells me, because all of my numbers in that last row were either positives or zeros, weren't they? All of these numbers are positive or zero, tells me that the number 3 is the largest zero, nothing bigger. Part 2. If C is less than 0, and the number in the last row are alternately positive and negative, zeros don't count as positive or negative, then C is a lower bound. So let's say I chose -1. And again, I got some numbers here. I brought this number down, it was a 2, and this is -6, and this is 4, and this is 0. Are they alternating between positive and negative, or 0? Yes. This tells me that -1, it's a 0 because the remainder is 0, and there's no numbers smaller than -1 that are also zeros. -2 doesn't work, -3 doesn't work, -6 doesn't work. So if this problem though I just made up, I know the smallest zero is -1, and the biggest number, the biggest zero is 3. It's all going to be right in through there. Does that make sense? Word problem. In a minute. Oops. Go back. Another hint to find real zeros. Before you start trying your synthetic division and everything, remember you have to have a constant at the end. Does it doesn't have a constant at the end? No. How come? So can I factor this? What's the first step you always do in factoring? Greatest common factor. Does this one have a common factor? Greatest common factor is? Greatest common factor is X, right? So before you start trying to simplify it further with synthetic division or whatever, first factor out that X. And this is what it would look like. X times X cubed minus 5X squared plus 3X plus 1. Now we can start working with synthetic division here. Keep in mind, this is still a 4-degree polynomial, right? Yes, no? 0 is one of the solutions, right? So that's not going to factor into, because when we talked about the cardinal signs a while ago, that was talking about negative and positive solutions. There wasn't anything about 0 solutions, right? So there it is right there. The remaining zeros can be obtained by analyzing that cubic. Whatever method we're going to try. You're designing candle making kits. Each kit contains 25 cubic inches of candle wax and a mold for making a pyramid-shaped candle. It's going to be a square pyramid. You want the height of the candle to be 2 inches less than the length of each side of the candle's square base. What are the dimensions of the candle going to be? There's your whole problem right there. That's it. To solve this, first of all, we need to know what the volume of the square pyramid is going to be. What's the volume of the square pyramid? 1/3 BH, right? What's capital B mean? Area of the base. What's the shape of our base? A square. What's the area of a square? Length times width, but if it's a square, huh? Length squared or x squared. Okay, so we know that the area of the base is x squared. It tells us the height of the candle is 2 inches less than the length. Well, if the length is x, then the height has to be x minus 2. This all makes sense. So our formula is going to be 1/3 x squared times x minus 2. Here it is. The volume is 1/3 times x squared times x minus 2. They tell us that we have 25 cubic inches of wax. So there's the volume. So we're going to change the V to 25. Y'all hate fractions. So that's a fraction. Y'all hate fractions. So to get rid of the fractions, we multiply both sides by 3. 25 times 3 is 75. 1/3 times 3, it's gone. X squared, oh, they've distributed. I hate how they skip steps all of a sudden, right? Oh, no, they said they did it. Okay, so they multiply each side by 3 and distribute the x squared gives us 75 equals x cubed minus 2x squared. Put it in general form, meaning set it to 0. Now what? Factor. No. So now we have to factor this. Okay, I'm not going to mess any time with factoring that. Using the rational zeros theorem, the possible zeros would be, now notice that the leading coefficient is 1, so my A is 1, which is a good thing. So all I need to worry about is my P. What are the factors of 75? 1 times 75, 3 times 25, and 5 times 15. All of them are plus or minus, right? I am talking about the dimensions of a candle. Will the dimensions of the candle have a negative number? No. So we can automatically, we're going to throw all those away. At this point, I have a polynomial. And I have 1, 3, 5, 15, 25, and 75 to use as numbers. And I'm going to do synthetic division. That's what we're going to do. Okay? So we would try 1, find out it doesn't work. We could try 3, it doesn't work. Try 5, 5 works. What does that tell us? So x is 5.
Yeah, okay, so with the even thing on like the last slide, where it was like if it all equals out all even, that thing where it's the odd, if everything is all odd, it's the highest or lowest that it's good.
If I wrote all even and odd numbers, that was not intentional.
No, like you know how keep going back the whole before this. Like the whole chain like this, right? You know how it's all even?
Nice. Same thing. They're all positive. They're all positive or 0.
Okay.
They're all positive or 0.
I thought it meant they were all even.
Okay. You know, when I'm making up stuff, I don't even pay attention to what I'm writing down. As far as odds and evens, I just write down numbers. It just so happens those all happen to be even. Okay. So I know that 5 is 0 this, and this makes sense now. So 5 is a solution, so 5 is the length of the base. How tall is it? How tall is the candle? Go back to the question. 7. So how tall is the candle? 3. Right? So by finding x, we know all the dimensions of this square pyramid candle. This candle has a base of 5 inches by 5 inches, and it has a height of 5 minus 2. It has a height of 3 inches. And there it is. Okay, so this particular function, once let me go back real quick to this last part. Once we found out that 5 was a solution, remember this was a cubic, right? It started off being a cubic, 1, 2, negative 2, 0. There's no x's, that's why that 0 is there. So this was a cubic, makes this a quadratic. X squared plus 3x plus 15 does not factor. If you plug those numbers into the quadratic formula, you find out that the other two solutions are imaginary. Can we have imaginary bases? Great, says yes, no. So the other two solutions to satisfy that are imaginary, and we can throw those away. Just like if, what if we had a solution that was negative? Throw it away. Can you have a negative link handle? Okay, so the only things that work for us are positive numbers. Okay, and that is it for 3, 4, right? Here we go with 1, 8. Huh?